So Bruce, a lot of your work has been about trying to predict who's going to reject their kidney and who's not. And you were telling me before that lots and lots of different things can make a good prediction, but altogether they don't work. What's the story?
So the easy answer that I've used is that we do two steps in biomarker development. We have a discovery phase, and then we have a validation phase. The easy answer I've used is that we are relying too heavily on the discovery phase. In the discovery phase, particularly this day and age of what we call multidimensional molecular biology, we have thousands of molecules to choose from, be it they transcripts, microRNAs. So when we use discovery, we're saying, here's the endpoint. Which ones predict that endpoint best?
So you have 1,000 variables between people who reject and don't reject, and you say, how are they different? And guess what? There's always differences.
Yeah, and it's a multiple testing issue, and we almost always discovery will look good.
Mm-hmm.
So my original thing I would always say was, it's the lack of rigorous validation that has left us without a biomarker yet that we can use.
That might have been 20 years ago?
Well, it started over 27 years ago.
Okay.
And we're still in search for that biomarker. So it made me realize that perhaps that easy answer, that it's not just lack of validation.
How many studies have been done looking for biomarkers of who's going to reject?
Hundreds.
How many are used routinely in clinical practice?
None.
Please explain.
I wish I could explain it to you any better than saying that perhaps, and I use that Tolstoy quote, perhaps, all happy grafts are the same, but all unhappy ones are different in their own way.
Happy grafts, happy transplants.
Happy grafts, happy transplants.
Yeah.
But
that's a different idea for me as a doctor. I mean, I would have expected that the physiological and cellular and genetic mechanisms that induce rejection would be the same in everybody.
And so that's one explanation. The other is, as we talked about before, is that there's enormous ambiguity in each molecule. That take a molecule like IL-1, which is supposed to be pro-inflammatory.
Right.
It may increase inflammation under certain conditions, but it may decrease inflammation under other conditions, depending what other
So we'd like the system to
around.
be simple, so we can have multiple choice tests for our students. Is IL-1 pro-inflammatory, anti-inflammatory? And it's not that simple.
And unfortunately, it's not that simple. It's a system that works as a concerted mechanism, and the action of any one molecule is dependent on the other molecules around it.
So this comes very close to one of my hobby horses, Bruce. I talk a lot about what I call organic complexity, because the kind of complexity in bodily systems that have been shaped by natural selection, I think is fundamentally different from the kind of complexity in design systems. If you were designing a group of cytokines to interact with each other through a bunch of different kinds of white cells, you would have each one have a function and each one connect to itself in something else, but that's not the way the system is that right?
It doesn't appear to be, and experimentally and empirically doesn't seem to be that way.
They all interact every which way to make it happen.
And yeah, so I think the classic, and excuse the more fancy language, of the Aristotelian deductive model, where we remove all...
Aristotelian deductive model, so say more.
Well, a lot of modern medicine is based on Osler.
Okay.
And if we think back to Sherlock Holmes. Sherlock Holmes was based on Osler.
I didn't know that.
And it's based on the deductive model. So in the deductive model, we want to prove causality.
Find the criminal.
Find the criminal. And the way in a deductive model, we say, if we look at A, we can prove A caused B if we remove every other possibility. So the only thing left could be A.
That's how I was taught to do experiments. You hold everything constant, change only one thing, and see what else changes.
And that's the way we've done science for the last 200 years, and it's served us well in many areas. The one place it maybe hasn't served us well is in explaining how systems work.
Oh, say more.
Well, in the deductive model, we're assuming that molecules live in isolation because we want to remove confounders.
Mm-hmm.
We want to deduce by deduction.
So changing one thing should change one other thing, but it doesn't.
But it doesn't. And it may do that if you could remove all the other molecules.
So if
But in the
you,
human body, we don't have the luxury to remove all the other molecules.
or even in the physiology of a bacteria.
Or the physiology of bacteria, or any natural system.
So this is so profound, actually, that the structure of complexity in living things is different from the structure in design things. And as doctors, we teach our students, they memorize the Krebs cycle, and they memorize the clotting cycle, and they memorize the different arms of the immune system and what each different kind of white cell does, except none of it's quite true.
I'll disagree only slightly with you, Randy, that it is true if you understand the system on which it was proven.
Okay.
It is true in isolation that that is the case.
So they're facts that are true if they stand by themselves.
If they stand by themselves. So it is true if you were to use the same mouse model of inbred mice with homozygous for every other, no heterogeneity of any other molecule.
Right.
And if you were to look at that, it probably would be true and reproducible. But when we deal with patients and the natural world, we can't do that.
Right.
So I don't want to make it sound like the scientists falsify data. It's true under the conditions on which they do it, but those conditions may not be the conditions that life live, that we live life.
We try to make things simple enough so we can create test questions
Right.
for our students.